Thank you very much. So, do you hear the microphone? Yeah, it's working. Okay, good. So, thank you very much for organizing this wonderful conference. So, the title is General. So, I will talk about this general theorem and show you some of the applications to algebraic groups. Yeah. So, this is the connection to the conference. And I gave this conference once in front of Jean-Michel, and then he decided to suggest me for this conference. So I hope you'll also be convinced that there are some techniques in computational algebraic geometry that would in principle be interesting here. So, okay. So as announced, the talk is about Chevalley's theorem. This theorem was originally proved by Chevalley, but his original proof had some flaws. There is a complete proof in Grothendieck, and it indeed has a computational content, but when you translate this into an algorithm, it's not efficient enough. So my colleague Markus Lange-Hegermann and I sat down and came out with a more efficient proof than the ones in the literature. And now there are many, and they all have a computational content, but they don't perform good enough on the computer. Nevertheless, the main induction step, the main induction scheme of the algorithms, of all these algorithms, are more or less the same. It's only the details will be the difference in the induction step. Yeah? So let's start at the very beginning. So consider the polynomial map over some field K, and then take the first nonlinear map you can think of from A2 to A2. You see already in the first argument it is linear. It's even the identity in the first argument. And in the second argument it's mildly nonlinear. Yeah? So it's just quadratic, the most simple thing you can think of. And now we want to understand the image of this map. So to do this, so it's a map from A2 to A2. If you want to draw this as a graph, you need a four-dimensional space, which is a bit tricky. So what you do is you simply write down in the codomain a grid, and then try to understand the effect of the map on the grid. Yeah? And what you quickly see, because of the second component of the map, that the horizontal lines of the grid are tilted through the origin, all of them. And the vertical lines are rescaled in place. Yeah, so just rescaled. And only something interesting happens at the origin, that this b axis is shrink to 0 because of this x here. Okay? So now I can ask you what is the image, and you can read it off from the picture. So the image of f is, in the first approximation, the entire affine plane. So this is the codomain of the map. Still, you have to remove the b axes given by the equation a equal to 0. But this would be too much, and you have to add back the origin, right? The origin is met by all the horizontal lines. They all pass through the origin. They're all mapped through the origin. Okay, so this image is neither closed, as you can see. It's neither closed in the Zariski topology, nor open. So this would be closed. This would be open. But then you have to add something else. And you cannot really simplify this any further. So it's not even open and not even locally closed. And then I'll define what locally closed mean on the next slide. So it's something more complicated. But still, you want to describe it in an algebraic way. So let Y be a topological space, fairly general. A subset A of Y is said to be locally closed if one of the following equivalent descriptions hold. So the first one is the one giving the name. It's an intersection of an open and a closed. So this is closed in open, locally closed. Yeah? The next one will be the one we will be working with on the computer. It's the difference of two closed subsets. And now you just take the complements, and you see this is the same as the difference of two open subsets. And now we introduce this new notion, the notion of constructible, so new for the slide. So a subset A is called constructible if it is the finite union of locally closed sets. And now we can see that the image of F is constructible in Zariski topology, right? This is closed without closed, union closed without empty. So it's the union of locally closed, right? And in fact, it is exactly the statement of Chevalley's quantifiers elimination theorem, which says that images of rational maps of affine varieties are constructible. This is the one we are aiming at. You can drop the affine and then deduce everything from this theorem. So this is the one that generalizes to more arbitrary maps, so to maps between affine varieties. Yeah, but they all boil down to show this one. And the novelty of our proof is that we are working with spectra, so we do not require fields, and we do not even require algebraically closed fields. Yeah. Okay, so this theorem is usually formulated for algebraically closed fields, but nevertheless, we're working over spectra. So if you would have a field, you're implicitly also having the all extensions, all finite extensions above it. So this is in the word spectrum. Yeah, so I'm not claiming that I have this quantifier elimination for real fields. Yeah? Okay, but the difference is now that I also can work over Z, yeah, not just fields. So let's proceed. An example which would be interesting for this conference is looking at the an action of an algebraic group, in this case an affine algebraic group, acting on an affine variety. And then we see that the group orbit is constructible. And once you know that it's constructible, you can even prove that it's locally closed, because it is the image of this orbit morphism. So you restrict your action just in the second component to y0. And then the image of this restricted map is exactly the orbit. Yeah? So you now have, in this case, a polynomial morphism, which is in particular a rational morphism, and the image of this is the orbit. So you know by Chevalley it's constructible, and by equivariance you can prove that it must be even locally closed. Okay? So here is the most simple example I could think of. So you can maybe do this in linear algebra 1. So you can take the SL2 K over an arbitrary field, which acts on the traceless matrices. This is the Lie algebra. And the action is the adjoint action. So in this case, it's just the conjugation. And then you ask about the orbit of the nilpotent matrix. So this is this Jordan form, the Jordan block with 2 by 2 Jordan, non-trivial Jordan block with 0 eigenvalues. And you know, but by this application there, that the orbit is locally closed. And indeed, you know that conjugation does not change the trace. So the trace of this is 0, and the determinant is 0. So these two will remain. But this is still too big, because the 0 matrix fulfills this. And indeed, if you remove the 0 matrix, you will get precisely the orbit. Okay? Good. So here you see on a very simple example that the orbit is locally closed. So the central idea of any proof in the literature of Chevalley's theorem is to exploit the inductive nature of constructible sets. Yeah, and this is what I will be explaining on the next slides. So our central definition, which somehow clarified the picture of all the proofs, is this notion which we were not able to find in the literature, but maybe it's there somewhere. So the relative boundary of A is defined as the boundary of A in its closure. So imagine now this is my space Y, and I take the subspace A to be this punctured line. When I ask you about the boundary of A in Y, you will tell me it's the closure of A. But now I want something relative. I want the closure, I want the boundary of A relative to the closure. Yeah, so in some sense, I'm replacing y by A and then asking for the boundary. And in this case, I'll just get this point, which is more interesting. Yeah, it's telling me that the line is missing the point. Okay? So this is the formal definition. So it's the closure of the complement of A in its closure. Yeah? And to see what this has to do with the classical notion of boundary, we rewrite this. So I have to point probably here. So this is just a simple rewriting. And you know that the closure of the intersection is included in the intersection of the closures. So I just have one direction here. And the right-hand side is simply the definition of the boundary. Yeah? So you see that the relative boundary is included in the classical boundary. So now comes actually the notion which is relevant for the induction. It's called a relative boundary hull. So a relative boundary hull D of A, provided A is non-empty, is a closed proper subset of the closure, such that it includes all the extra points which are in the closure but not in A. And because this D is assumed closed, it will also include the closure of the extra points, so it will include the relative boundary. Okay, and then this was defined just for non-empty sets, and then you complete the definition by saying the relative boundary hull of the empty set is the empty set. This is the corner case. Yeah, and this will happen when your induction terminates. So this is a word of caution. Of course, every set has a relative boundary, but not every set has a relative boundary hull. And here is a simple example, not in Zariski topology, but in classical topology. You'd look at Q as a subset of R. And in this case, you quickly see there is no relative boundary hull, because in this case, the closure and the relative boundary coincide. So there is no place in between these two, right? There is no place in between these two. I cannot find a proper subset of the first because these two are already coinciding. Okay? So, but this is of course not the topology we will be working in. So we can say if a relative boundary hull D exists, then the relative boundary is the minimal such hull. And this gives the name. It's a hull for the relative boundary if it exists. Okay. So let's proceed. So again, if A, this is again the sanity condition, if A is a non-empty set of Y, and if it admits a relative boundary hull, which we know it's not always the case, then it includes a non-empty locally closed subset. And this looks very much like the beginning of an induction. So we now can take A, in our case it will be the constructible image, and chop off something which is locally closed. This is closed minus closed, right? And this gave us the idea to reformulate Chevalley's theorem in this way by saying this is Chevalley's quantifier elimination theorem reformulated. The image of a rational map from X to Y of affine varieties admits a relative boundary hull. And now you can easily use this reformulation. This is just the induction step to prove inductively theorem 1. So you proceed as follows. You know now by theorem 2, this is just the induction step, the image f of x admits a relative boundary hull D by theorem 2. And then you start writing the image f of x in the following way. You say that it's the closure without this hull, which is guaranteed by theorem 2. But this is too big, and now you have subtracted something. So you correct this by adding back D. If you add back D, you will get the closure. This would be too big, so you have to intersect this with the image. Okay? The good thing is now that this is here locally closed. This is closed minus closed, right? So it looks as if you're beginning to do something, but this looks weird. And we have to rewrite this. And the rewriting is the so-called projection formula. You know that maps behave bad with respect to intersection. So the image of the intersection is just included in the intersection of the images. Yeah, this has to do with violating injectivity. Yeah, so for example, if you have 2 points, yeah, and they map to the single element, if you take their singletons and intersect them, you get the empty set. So this maps to the empty set. But if you map them first and then intersect, you will get something, right? But this formula is good if one of the sets is a pre-image. And this is exactly the trick. This is the whole idea of induction, that you rewrite the second term in this disjoint union using the projection formula. And then you know that you can now apply f to the smaller, strictly smaller subset of x. Yeah? And this is exactly the induction. So we now can concentrate our effort in proving that we have a relative boundary hull. Okay, the induction is already done. Good. So to emphasize more the inductive nature of constructible sets, we found a canonical decomposition, which we were not able to find in the literature. And actually, by now, we can even compute these to decide the equality of 2 constructible sets. So we define the locally closed part A of A in some topological space Y is defined to be the closure of A without the relative boundary. So if you would look at this here, you will take the closure of A without the relative boundary, so you will recover A again. Yeah, so this will be the locally closed part of A. And indeed, in this case, A is locally closed. So you get a canonical form for a constructible set as this disjoint union. You start by approximating A by this locally closed part of it. And then you take the locally closed part of A without the locally closed part, and then you induct. And this gives you a very nice canonical form for constructible sets, which terminates if your space Y is Noetherian. Noetherian means that you have the descending chain condition for closed subsets, yeah, which on the ideal level will be the ascending chain condition, and this explains Noetherianity, although it's only in one direction. So in this sense, the locally closed part of A is the largest locally closed subset in A, and you see this is a sort of greediness. Yeah, you're going and chopping off the largest locally closed part, removing it. What you get back is constructible. Then you remove the largest locally closed part, and so on. And you're doing this in a way that you get even a disjoint union. Okay. So this illustrates the inductive nature of a constructible set, which you already saw in the induction of the algorithm. But this here is the most greedy thing you can do. So here we're subtracting this, yeah? And this is usually bigger than if you just subtract a relative boundary hull, right? So this would be the most greediest thing you could do, but in the algorithm you cannot get this on the nose, yeah? So you just are happy with a hull, with a relative boundary hull. Okay, this would be the best thing. So this would be the smallest, and this means this would be bigger than that. Okay. So the goal is to develop a geometric proof of Theorem 2, the existence of relative boundary hulls for images, which directly compiles to algebra. And we will implement, and we have implemented this algorithm simply in this geometric terms. And we have enough software that does the compilation to algebra ourselves. So we do not write Gröbner-basis algorithm. We write exactly the algorithm as you will see on the slides, completely geometrically. Yeah? And the software takes care of compiling this to algebra. So we start by a very simple observation. Instead of looking at all maps, we want to restrict ourselves to projections. And actually, this remark is from school. Yeah? If you want to study images of maps, you just write down the graphs and then project the graph down to the codomain. Okay? The only thing is that we're switching the role of the axes so that when we project down, we don't project horizontally. Yeah? Okay, so the image of the map, so here you write down the graph, and the image under the projection is the image of the map. So now you can say, equally general, we can consider projections of arbitrary gammas, regardless if they're a graph of something or not, right? But then again, this is not really more general than F, than this situation, because you can say, again, this is a map, right? It goes from y cross x to x, so it's again a map. Okay? But this situation simply is nice. We have here a fibered space. It has more structure, and we're dealing just with one sort of maps, just projections. So if our setup is affine varieties, which is the case, then we can think of x embedded in some affine space, y embedded in another affine space, and we can view gamma as lying in the product, which is in this case also an affine space, yeah, of the dimension being the sum of the respective dimensions. And now we can extend the pi to be the standard projection along the fibers, right? We're just chopping off the coordinates of x. Good. So now this is our setup. We want to find relative boundary hulls for pi of gamma. So if gamma is the vanishing locus of some I, this is the definition of Zariski closed, right? It's the vanishing locus of some ideal, where I is an ideal in the coordinate ring of the fibered space, AM cross AN. Then pi of gamma is the vanishing locus of the ideal I intersected with the subring B. And I hope you can see that this cannot be true, because the right-hand side is a vanishing locus, so it's closed by definition. And we just saw examples where the left-hand side is constructible. So what is missing is the closure sign here. Okay, so we see on the right-hand side an operation, an algebraic operation. If we can do this algorithmically, then at least we can get the closure of the image. But of course, we want the image and not just the closure. So how to compute the intersection to be able to compute at least the closure? So this is an intersection of an ideal with a subring. And this is standard. This is called elimination. So you have an ideal in the polynomial ring. You take a global elimination order, which eliminates x. For this, you can take a block elimination order or a product order. And compute the Gröbner basis of I with respect to this elimination order. Now G is finite. And now you intersect this finite set with the subring. Yeah? So you just inspect your Gröbner basis elements. Which of them do not include the variables x? Yeah? And only those in B are the ones you retain. And you figure out that this here is actually a Gröbner basis with respect to the restricted order, to the subring. So you don't need to compute a Gröbner basis anymore. So let's do our example from the beginning. So I am computing the, you remember this was the image of the map. So the map was this, xy maps to AB equals to x and then xy, the identity in the first coordinate and mildly nonlinear in the second coordinate. Yeah? And the image looked like that. So the origin belongs to the image and then everything else. Yeah, and you see the closure is the entire affine plane. And let's check this. So as we said, the image is the the image closure is the projection closure of the graph. And then I write down the ideal defining the graph. A is equal to x, B is equal to xy. Put this in an ideal. And then intersect with the subring. And you look at the elements of the ideal, and you see no consequences for A or B, right? So this means the intersection is the zero ideal. And the zero ideal, the vanishing locus of the zero ideal is the entire plane. Yeah? So you've verified that the closure of the image is everything. So let's look at another example. This one is instructive. So this is actually our main example. Yeah? This gives all the ideas. So look at the hyperbola. You can view this gamma. So first of all, it's not the graph of a polynomial map, although it's a graph of a rational map. Yeah? So you map x to b equals 1 over x. Okay, and when you write the graph, you get out the principal ideal bx minus 1. Okay, and now you do the same algebraic computation. You want to compute the image of gamma, so before you even compute, you know what will come out. Yeah? So if you project, the image will be everything except the origin, but you're forced to take the closure by the algebraic operation we're doing, right? So you will get everything. So you accept again the zero ideal. So write this down, the vanishing locus of this ideal, bx minus 1, intersected with b. So you ask yourself, does this have any consequences for b? The answer is no. So the intersection is the zero ideal in kb. And this is indeed the affine line, which is this b exes. And because of this example, I can now ask you the following question, which just disappeared. So it's already here. So where do the extra point come from? But I need the graph. So we got this point extra. Do you have an idea where this point comes from? Yeah? It's coming from infinity. And this is what we will be proving on the next slides. This is everything. This is the entire idea, that the extra points are coming from infinity. So we want to prove this. We have a guess. So you now look at the embedding of gamma in this fibered space, and then you start closing the fiber projectively, because you want to go to the infinite points, right? So we take now the projective closure of the fibers, and we do the same for gamma. And we define gamma hat. So gamma hat is the fiber-wise projective closure of gamma. Okay? And then you extend the projections. Pi now becomes pi hat. Okay? It simply maps the entire fiber again as it did it for the affine fiber on the corresponding point. So this is easy. And the difference is now that pi hat is a closed morphism. So it maps closed sets to closed sets, unlike pi. Yeah? This was actually the problem of pi. We had something which is closed, and it was mapped to something which is constructible, not even locally closed. Yeah? But pi hat is a closed morphism, and this is called the main theorem of elimination theory. So hence we can say the image of pi hat of gamma hat, this guy is closed, so this is closed by the main theorem of elimination theory. So gamma hat is the closure of gamma in the bigger space. So I can write here, instead of gamma hat, gamma closed. Pi hat is a continuous morphism of affine varieties, so continuous with respect to the Zariski topology. So I can get out the closure. And now pi hat is as good as pi when it comes to gamma. So I can replace pi hat by gamma, and now you see what happened. So when I computed this, I was computing the image of this bigger set of the fiber-wise closure under the extended projection, right? Okay, so now we can draw consequences of this to get a candidate for the relative boundary H. So let's do this. We start with the extra points which are annoying us. We want to get rid of them, yeah? So now simple set theoretic consideration, yeah, by the previous three equalities we had, you can prove these inclusions. And now you look at this middle term here and try to understand what this is. So this here is, I'm sorry, I have to point at my laptop. So these are exactly the points at infinity. right? You're taking the gamma hat and you're removing the affine part of gamma. And what is remaining are just the points you added at infinity. So we call this gamma infinity, and we write it down here. Okay, so we have actually already proved that the extra points are coming all from infinity. And now we proceed a bit further. This gamma hat was a difference, but actually it can be written as gamma infinity is a difference originally. Yeah? But now we can prove, we easily see that it is gamma hat intersected with the hyperplane at infinity. So it's the intersection of two closed, so it is closed. And if this is closed by the main theorem of elimination theory, the image is closed. So this looks good. Yeah? This is a candidate for what we would like. This is something like a D. And indeed, we would have a proof of theorem 2 if this last inclusion here would be a proper inclusion. Then we would have exactly the definition of a relative boundary hull. Right? And now, where's the problem? The problem is that if you take exactly the same example, but now view it in 3 dimensions instead of 2 dimensions. So you now take the hyperbola and take the cylinder over the hyperbola. Okay? Before that, we had A1s, in them just points. So when we closed the A1s, we still had points. So the points could not escape to infinity. But now if we have the cylinder over the hyperbola, right, we will have A2. Inside of A2, the cylinder over the point, so we'll have a line, and the line will escape to infinity. So this is extremely bad, because then every point will come from infinity, and there will be no distinction anymore. Right? So this looks bad. This is a good idea, but this is a very simple example that destroys everything. And the idea is to rectify this example by intersecting back. Get rid of the extra variable y. This is everything. And this is formalized on the next slide. So given such a gamma, there exists a closed subset gamma 0 of gamma, which is just intersecting with the plane y equals 0, yeah, to get the original example back. Gamma 0 has locally 0-dimensional fibers, as our original example. And still, the closure of the projections is the same. And why is this good? Because this implies that the extra points are trapped inside the closure of the projection of gamma 0 without pi of gamma 0. I mean, gamma 0 is a smaller set, so this is definitely a bigger subset, because these two here are equal. Yeah, and this is smaller than this one, yeah, in general. So you just get an inclusion, but this is not a problem. And by the previous consideration, this is included in this candidate for the relative boundary hull. But now we have a strict inclusion, because we know that at least one point, because of this condition, will not come from infinity. And that's all. And this gives us the proof of theorem 2. So where to get the relative boundary hull from? Pi hat of gamma 0 hat is a relative boundary hull of pi of gamma. And that's all. Okay, so this is the entire proof. And our relative boundary hull is more efficient, so it's much more smaller than the competitors, than Chevalley and Gröbner-basis and other people who wrote down a proof, because they had a different strategy for the induction step. Our focus was to make the D as close as possible to the relative boundary, as small as possible, whereas they were trying to let F behave very nicely over the complement. Yeah? And the nicer F behaved, the smaller this set became. Okay? And then the less efficient the algorithm, because you needed a lot of branching, a very long induction, and this resulted in an explosion of everything inside the algorithm. Okay? So I can now give you the geometric proof in terms of an algorithm, and then show you line by line how this compiles to algebra. I don't do the compilation. I program it the way you see on this slide, and the compilation is done automatically like in the next slide. So compute the constructible projection in geometric. So this is now Theorem 2 with the induction scheme. So this is the proof of Theorem 1. And you will see inside it exactly how Theorem 2 is functioning. So take gamma to be a subset of the product, a closed subset. And the output is the projection of gamma, which we will call C, as a finite disjoint union of locally closed subsets. So here's the algorithm. You start by initializing C to be empty. And while gamma is not empty, do the following. Pass from gamma to gamma 0 to avoid the cylinder over the hyperbola. Right? Compute the closure of the projection of gamma 0. This is done by elimination. This is the biggest bottleneck of the algorithm. And then compute the relative boundary hull, which has this funny name, pi hat of gamma 0 infinity, as you could have guessed, maybe. And now you add to C this locally closed set, closed minus closed. And now you go into the induction and just look at the points in gamma, so the points in gamma which lie above the relative boundary hull. So you take the pre-image under pi of the relative boundary hull. So this is a restriction, and of course everything terminates because you have a Noetherian topological space. And then you return C. And when you compile this into algebra, which I don't do, the computer does this automatically, it looks like this. So this is the algebraic version. Take an ideal. Gamma is V of I. A finite list. The output is a finite list of pairs of ideal. Yeah, so the pair will be, the constructible set will then be V of I1 without V of J1, union, even disjoint union, V of I2, etc. So you start with the empty list. While 1 is not in the ideal, this is corresponding to gamma not empty. Pass from I to I0. This is the passage from gamma to gamma 0. Compute a Gröbner basis. This is the closure of the projection of gamma 0 with respect to block elimination order. Yeah, this is one step. So yes, this is the elimination. So this step is the closure of the image. And now you're computing the relative boundary hull by doing the following. You take in gamma 0, in G0. So here you just look at only those polynomials with which are just in B. And here you take all of them, also those having x's. And you take just the maximal degree parts in the x. These are now homogeneous. You saturate this guy out, this ideal. And then you get an ideal in B again, because you're setting x1 till xn equals 0. Okay, so you'll get back an ideal inside KB. This will give you the relative boundary hull. We can see that the computer does this in the background. We don't care about these details. This is automatic. And then we add the pair I pi and I infinity to the list until yes, and now we look at the projection. You see I'm not really fluent in the algebraic language because this happens in the background. So you add to the ideal I infinity. Yeah. This is restricting to the pre-image of the relative boundary hull. And then you return C when I is the unit ideal. Okay, so how much time do I have? 10 minutes. So this is maybe enough to show you some software. Good. So this is a Jupyter notebook. This is one like Nicolas Thierry was using in his talk. I'm using a software called GAPGL. This is, so yes, behind this is Julia. This is this modern programming language, which is the language around which we're developing Oscar, hopefully the new Magma. And below Julia, or in Julia, there is a package called GAPGL, which was masterminded by one of my postdocs, Sebastian Gotcha and Max Hahn, who is here in the audience, and with contributions from other people. And you will see that the software is calling other packages in GAP. One of them is this HOMAG project, and this will call singular. Okay? So for the Gröbner-basis machinery, we will be calling singular, and you will see the explicit invocation of singular in the on the slides. So I'm loading the HOMAG project, which is, yes, this is Jupyter, so I have to press Shift-Enter. So this takes a while. I'll just do this on the first example, and then I'm loading the package called Zariski frames. This is the package in which I have implemented this algorithm, Chevalley's theorem. This also takes a while. And then I can go to the next slide. And now, as you see, I'm defining the HOMAG field of rationals in singular, and because I'm using Julia, I can write Q in this very fancy way. Okay, and you see that I'm invoking singular, a fairly recent version. And now I can construct the coordinate ring of the base. I can construct, or the codomain. I can construct the coordinate ring of the domain. And I can construct, this is the base, right? This is the coordinate ring of the base, and I'm now constructing the polynomial ring over the base ring. So this is QBX. And now I'm writing down the equation for the hyperbola. And if I display it, I see this is the vanishing locus of the graph of the hyperbola, of the ideal of the hyperbola. So I then go and then compute the constructible image. And it's telling me that it's locally closed. So it's closed without closed, and I can display it and see it's everything without the origin. See, the vanishing locus of the empty ideal, this is 0 without this. So now I can visualize the computation internally, and internally it constructed, internally it constructed the closure, and then it subtracted in the second step the origin. Okay, you see here the closure has dimension 1, and it's subtracting something of degree 0, of dimension 0. Okay, so we can now do this for the hyperbola in 3D. I've prepared this, so we don't need to wait. I even started singular, and now if you do it, now you see we have one more variable, one more fiber variable called y, which does not enter the equation. And if I display this, you don't see a difference. And I can compute the constructible projection, and I get the same. Okay. And if I visualize this, I see I just needed again 2 steps. This is the original example I started with. Yeah. This one here of the mildly nonlinear map. And the base space has the coordinate ring QAB. The target, so this is the B is the codomain, now this is the domain, and now I define the ring map, and I can display it. It's the map that I just wrote here, and it's written here ring theoretically. Ring theoretically, things go from the bottom to top, and scheme theoretically, you go downstairs. Yeah? So I view this scheme theoretically. I think of this as the spec going down to the spec as a projection. And now I compute the constructible image, which uses the constructible projection. And you see in this case it's not locally closed, it's constructible. Yeah, and you see it's the entire affine plane without the BXC's union with the origin, without nothing. And if you visualize it, you see that he needed 2 steps. So this is the first induction step, and then this is the second step in the induction, and there was no thing he needed to subtract. And then I go to the next slide. This is the Jordan example, and here I've defined everything, but now the difference is that I'm now taking Z, so I want to look at Jordan in every characteristic. Yeah, so we have defined, we have proved Chevalley not just over fields, but over affine rings, and affine algebras. This allows us to work characteristic free. And I can define the input for my Jordan problem. So I don't know what's happening. Probably I have to restart. Please? I did not evaluate the intermediate slide, so let's go back. Ah, thank you. Thank you. So here, thank you very much. So it's a matrix G, B, and this is the map, of which this is the orbit map that appeared on my slide. So it's a homomorphism, and this is the homomorphism where the image of it is the nilpotent cone. And now I can compute the constructible image of the map. It is locally closed, and I get everything without the zero matrix. Right? Trace 0. Here you see the trace 0. Here you see that the determinant is 0. It's simplified with respect to the trace, yeah, and then without the zero matrix. And if I visualize this, I get that here. But in fact, he did internally an induction. So he added a three-dimensional. Remember, we're working over spec Z, so there is one more dimension coming from from spec Z. So he added the closure, subtracted something, which he figured out he has to add back again. So the double arrow means equality. And then he had to remove the origin over spec Z. Yeah? And the A here means the active. So at the very end, he had to just take this and that and prove that it's locally closed, which we already know by theory. So this is an example from my colleagues in quantum information theory. They're interested in orbits of algebraic groups on different spaces. So this is the automorphism group of the P1 of the projective space in dimension 1. The projective space is the Bloch sphere in quantum information theory, and this describes the states of a qubit. Yeah? So they have here 3 qubits, okay, and they want to classify the orbits of the internal automorphisms for 3 qubits. So they want to classify entanglements of 3 qubits, okay. And so let me see if I've evaluated everything. Yes, I read this file. So I want to compute the orbit of 2 elements in P1 cross P1 cross P1, and they have names. The first one is called the GHZ state, and the other one is called the W state. And this is also prepared. I don't need to click anything. So here the gamma, and now I compute the constructible projection. I get something which is locally closed. If I view it, I see it's everything without this here. This is the hyperdeterminant. It's just one equation. So this is a principal ideal. And this thing has a name. It's called the hyperdeterminant. If I visualize it, it's closed minus closed. But in fact, internally he did that. You see, he computed this and had to compute all the. So 2 layers mean 1 induction step. This is 1 induction step, 2, 3. Okay? And here you see how things collapse. So he computed the closure, minus this, minus this, minus this. Then he figured out he has to add these 2 back. This is the equal. And he collapsed them. So all these guys came on this level. And the 2 swallowed the 6 and swallowed the 9. But he has to continue with 7. 7 was added back again. And 11 was finally added on this same level, and 2 swallowed the 11. Okay? And this is the computation for the other state. You see also it's complicated. And this was our proof that our algorithms are way faster than our competitors. There are actually 4 different implementations of Chevalley's theorem. Here you can say that this is a corollary of this implementation. They didn't target the Chevalley's theorem, but if you have the Gröbner in singular, you can use it to compute the constructible projection. But we gave this system this example. So we're computing again the image of this polynomial map. It looks a bit ugly. And none of these systems finished in a month. Yeah? And our computation finished in 12 seconds. So maybe you can see here. I don't know how to, it's no slides because everything is big. So I'm defining everything. Here's the map, and here's the output. You see, it's here. You can see very nicely. It's the vanishing locus of this. It ends there without the vanishing locus of that. Union with the vanishing locus of this without the empty set. And here is the visualization of the result, and here's the visualization of the computation. And we could even go one dimension higher, where their computers exploded and our computer finished in 6 minutes, And you see how humongous the output is. You can't read it? Me neither. You see? So this was computed in 6 minutes. And the nice thing is you see that it's not locally closed by the very end, because you are adding one more locally closed set. Thank you very much for your attention. Yeah? So we're taking affine rings. So finitely generated rings over rings we can compute over. So over Z or over computable fields. Yeah? So, and these are the rings, all the rings we encounter in applications. Yeah?
Well, just a sort of a local remark, as we're in the Newton Institute. This business of the missing point coming from infinity can, to a slight stretch, be traced back to Newton's Principia.
Yeah, I believe this. Yes. You see, it's a very simple principle.
Yes.
And the example was more or less true, right?
Yes, he's playing around with GL3R, but he didn't understand the concept of a group, so he only used the elements of GL3R that he found useful. But anyway,
okay. But you see, just it's the hyperbola. It's the hyperbola.
It's all there. But of course, the computers that he used were used in his time, were based on ivory, and there wasn't enough ivory, so very few of them were made. But anyway, yes.
Okay.